While studying physics many years ago, my instructor posed this question. A rectangular block floats on the surface of a freshwater lake. A horse jumps onto the block, and the block sinks 12 centimeters. How much does the horse weigh? Solving this problem makes use of knowledge created by the Greeks over 200 years ago. Welcome to Floatation and Archimedes principle, where we investigate density and buoyancy. This knowledge is used today by marine engineers and ship designers, and we will use it to solve the horse problem. Before we start, a quick comment on units. In science and engineering, the terms mass and weight mean different things. Mass is an intrinsic property of matter, and weight is the force of gravity acting on an object. But the term weight is commonly used to describe mass. We say, for instance, that an apple weighs 500 grams, even though grams are units of mass. Recognize that regular procedures will require the units of force. It is a matter of common experience today that some objects float in water while others sink. Try and push a balloon underwater. You will feel an upward force that resists your push. When released, the balloon bounces back. What happens is that the applied force acts in a downward direction, pushing the balloon down, but the water exerts an upward force on the balloon, pushing it up. This upward force exerted by water on the balloon is known as upthrust or buoyancy. Ever caught a fish with a fishing line? When pulling the line, you will feel the fish weight in water is less than when it's outside. In general, an object experiences loss of weight in water due to the upthrust and is equal to the weight of water displaced by the object. Let us perform an experiment to verify this. We shall need a can with a spout, a stone, beaker, measuring jar, and a spring balance. Arrange the can and beaker as shown here, and pour water into the can until it starts overflowing. Once it stops overflowing, replace the beaker with an empty one. Suspend the stone on a spring balance and record its weight in air. Now lower the stone into the can containing water. Observe that the weight of the stone is gradually decreasing. Record the weight when the stone is completely immersed in water. The weight is less than in air. That is, there is an apparent loss in weight. Also, water overflows through the spout. Pour the water into the measuring jar and note the reading. This reading gives the volume of the water displaced. Since the density of water is 1 gram per cubic centimeter, the mass of water displaced is equal to the volume. This apparent loss of weight is equal to the weight of the water displaced. Thus, when an object is partially or wholly immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. This is called the Archimedes principle. Say for the fish weight is 4 kilograms in water, its approximate weight outside would be 5 kilograms. The water level has fallen too. The difference in water level will equal the difference in the weight of the fish in air and water. That is, weight outside minus the weight in water equals to the loss in weight. And this will equal the weight of the decreased water. This is because the upthrust is equal to the weight of the decreased amount of water. And so what causes upthrust? Now consider a solid of cross-sectional area A totally immersed in a fluid of density ρ as shown on your screen. Since pressure in liquids increases with depth, pressure of the liquid at the top T of the solid is less than that at the bottom B. Pressure of a liquid at a given depth acts equally in all directions, and therefore the pressure on the sides of the solid cancel out. If P is the atmospheric pressure, pressure PT at the top of the solid is given by PT is equal to P plus H1 rho G. Pressure PB at the bottom of the solid is equal to P plus H2 rho G. Since force is equal to pressure times area, force Ft acting on top of the object is given by Ft is equal to Pt times A, which is equal to P plus H1 rho G into A. Force B acting on the bottom of the solid, Fb is equal to Pb times A, which is equal to P plus H2 rho G into A. The resultant upward force on the solid is given by Fb minus Ft is equal to P plus H2 rho G into A minus P plus H1 rho G into A. Therefore, the resultant upward force is H rho Ga, where H is equal to H2 minus H1. This resultant force is upthrust U. Therefore, U is equal to HA G rho. But then H times A is equal to volume. Cross-sectional area times height is equal to volume, and therefore U is equal to V rho G, where volume V of liquid displaced by the solid is given by volume is equal to cross-sectional area times height. Mass of the liquid displaced is equal to AH times rho. Weight of the displaced liquid is equal to AH rho G. Upthrust is therefore equal to the weight of liquid displaced. The magnitude of the upthrust depends on the volume of the fluid displaced and its density. Upthrust in gases. Just like liquids, gases exert upthrust on objects in them. The upthrust in air is small owing to its density, but sufficient to make a hydrogen or helium-filled balloon to rise. The hydrogen in the balloon does have some weight, but the density of hydrogen is lower than that of air. Since the balloon is lighter, it rises in the air. If the balloon is filled with air, the air inside is neither lighter nor heavier, but the balloon fabric makes it heavier than air and it sinks. One example: a stone weighs 2.0 newtons in air and 1.2 newtons when totally immersed in water. Calculate A, the volume of the stone, and B, the density of the stone. Take G to be 10 newtons per kilogram, and density of water is 1,000 kilograms per meter cubed. Solution: volume of the stone is equal to the volume of water displaced. Again, apparent weight loss is equal to upthrust, and it's equal to the weight of the displaced water. That is 2.0 newtons minus 1.2 newtons, which gives us 0.8 newtons. That is the upthrust. The displaced water then weighs 0.8 newtons, and this is equal to 0.08 kilograms when we divide by 10. So how much volume is this? Density is equal to mass over volume. and therefore volume is equal to mass over density. That gives us 0.08 kilograms divided by 1,000 kilograms per meter cubed, which gives us 8 times 10 to power negative 5 cubic meters. This is equal to the volume of the stone. B. Density of the stone. Density is equal to mass over volume. Mass of the stone is equal to 2 newtons over 10, which gives us 0.2 kilograms. We have its volume, 8 times 10 to power negative 5 meter cubed. Density is therefore 0.2 kilograms over 8 times 10 to power negative 5 cubic meters, which gives us 2,500 kilograms per cubic meters, which is also equal to 2.5 grams per cubic centimeters. The law of flotation. Whether an object sinks or floats on a fluid depends on its density relative to that of the fluid. Density is defined as the mass per unit volume of a substance. If the object's density is less than that of the fluid it is put in, the object floats. If the object's density is more than that of the fluid, the object sinks. If we have water and glycerin, plastic balls and lemons, we place the plastic ball on water, it floats. Then we place it on glycerin, it floats too. Try the same with lemons. In water, it sinks. How about in glycerin? It floats. From this experiment, the density of the plastic balls is less than that of water and glycerin, and the density of the lemons is more than that of water, but less than that of glycerin. Let us put a ball in water. Let's pause. The ball and the water cannot be in the same place at the same time. The water has to move out of the way to make room for the ball. This is displacement, meaning being pushed out of place. So, as the ball goes down, it pushes the water up. Once the ball is completely under the water, it has all the space it needs. Then the water stops moving up. Whenever an object sinks or is completely immersed in a liquid, it displaces a liquid equal to its volume. What about when it floats? Does it displace its own volume? Clearly not. It displaces a lesser volume. Precisely, the volume of the liquid displaced only equals to the volume of the part of the object that is submerged. But there is something that is equal: weight. It would be interesting to note that the weight of the displaced liquid is equal to the weight of the object. This wooden block is less dense than water, so it floats, or at least it floats partially submerged. The submerged portion of this block displaces some water. Let us investigate this displaced water. We create the same overflow apparatus. Filling the tap over the spout, we will let water run out until it stops. The surface of the water is now level with the overflow spout. Before we start, let us weigh this wooden block. It has a mass of 266 grams. Our overflow tap is now ready for use. We have an empty cup on a scale positioned to catch and weigh the displaced water. The weight of the cup has been subtracted. When we lower the block onto the water, the displaced liquid starts to flow through the spout. The scale is weighing this displaced liquid. After a few minutes, the flow slows down and eventually stops. The scale indicates that the displaced liquid weighs 266 grams. Do you remember the weight of the block? It weighed 266 grams as well. The floating block and the displaced liquid weigh the same. This is not a coincidence. This is the law of flotation and is a special case of the Archimedes principle. A floating object displaces its own weight of the fluid in which it floats, or otherwise stated, the weight of a floating object equals to the weight of the fluid displaced. For this law to hold, the object must not sink, it has to float. By using this law, you can actually measure the weight of this ship. Note down the current water level. Put in the ship and note the new level. The water level has increased by 5 cubic meters. So by the law of flotation, weight of the ship is equal to the weight of the water displaced. Calculate the weight of the 5 cubic meters of water. Density is equal to mass over volume, and we know the density of water is 1,000 kilograms per cubic meters. Mass is equal to density times volume. Therefore, 1,000 times 5 gives us 5,000 kilograms or 50,000 newtons. This is equal to the weight of the ship. Let's take an example. Suppose the ship was floating in ethanol with a density of 800 kilograms per cubic meters. How much of ethanol will it displace? Solution: mass of the ship is 5,000 kilograms. Mass of the displaced ethanol is equal to the mass of the ship and is equal to 5,000 kilograms according to the law of flotation. Find the volume of ethanol that weighs 5,000 kilograms. Density is equal to mass over volume, and therefore volume is equal to mass over density. That is 5,000 over 800, which gives us 6.25 cubic meters. So you see, because ethanol is less dense than water, more of it will be displaced by the same ship. Obviously, we would expect the ship to displace less volume of glycerin owing to its higher density. Upthrust and relative density. The Archimedes principle can be used to determine densities of substances, both solids and liquids. Relative density of a solid. Relative density of a solid is equal to the mass of the solid over the mass of an equal volume of water. Since mass is proportional to weight, relative density can also be expressed as weight of the solid over weight of an equal volume of water. Note that when a solid is immersed in water, it displaces water equal to its own volume, and so relative density is also equal to the weight of solid over the weight of the displaced water. Again, according to Archimedes' principle, when an object is immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. So again, relative density can be calculated as relative density is equal to weight of solid over upthrust. Finally, the upthrust experienced by the object is equal to the apparent weight loss. Then, relative density is equal to the weight of the solid over the apparent weight loss. So to determine relative density of a solid, the solid is weighed in air and then totally immersed in water. Upthrust or apparent weight loss is calculated and the relative density determined from the formula above. Relative density is a ratio of two similar quantities. Mass is unitless. Tie the solid firmly with a thread and suspend it from the hook of a balance. Record the weight V1 of the solid in air. Place a hydrostatic bench across the left pan. Lower the solid in water and record its weight V2. Find the apparent weight loss of the solid. Calculate the relative density of the solid from the formula. Relative density is equal to V1 over V1 minus V2, which is equal to the weight of the solid in air over the apparent weight loss in water. For a liquid, repeat the same experiment using water and the liquid whose relative density you wish to determine. Find the apparent loss of the solid in water and liquid and calculate the relative density of the liquid using the formula. Relative density is equal to upthrust in liquid over the upthrust in water, which is equal to the weight loss in liquid over the weight loss in water. Take an example. A solid of mass 0.8 kilograms suspended by a string is totally immersed in water. If the tension in the string is 4.8 newtons, calculate A. the volume of the solid and B. the relative density of the solid. Solution. Weight of the solid in air is 8 newtons. Weight of the solid in water is 4.8 newtons. The apparent weight loss or upthrust is equal to 8.0 minus 4.8, which gives us 3.2 newtons. 3.2 newtons is equal to the upthrust and is equal to the weight of the displaced water. Because the solid is totally immersed in water, it displaces an amount of water equal to its volume. Let us find what volume of water weighs 3.2 newtons. Convert that into kilograms, divide by 10, and that gives us 0.32 kilograms. Density is mass over volume, and so volume is equal to mass over density. That is 0.32 over 1,000 gives us 0.00032 cubic meters, which is also equal to 320 cubic centimeters. This is the volume of the displaced water and it's equal to the volume of the solid. B. Relative density is equal to the weight of solid in air over upthrust. That is 8 over 3.2 newtons, which gives us 2.5. Before we wind up, let us go back to the question we began with. Rectangular block 300 centimeters long and 200 centimeters wide floats at the edge of a freshwater lake. A horse jumps onto the block and the block sinks a further 12 centimeters. How much does the horse weigh? Solving this problem needs us to think of the experiment we did earlier. We noted that the floating object displaced its own weight of the water. What happens if I add a weight to this floating block, like this 126-gram stone? The wooden block sinks further, displacing more water. Can you predict the weight of the water displaced by the stone? Did you get 126 grams? That's right. The additional weight of the stone causes the block to sink further, displacing a weight of the water equal to the weight of the stone, 126 grams. Now on the horse problem. We have a rectangular block measuring 300 centimeters by 200 sitting on a freshwater lake. A horse jumps on the block, causing it to sink 12 centimeters. Like the stone sitting on the wooden block, the horse has displaced to its own weight. We need to calculate the weight of this displaced water. The block, before the horse jumps, is sunk to this level. It has displaced water equal to its own weight. When the horse jumps out, it walks further placed by the weight of the horse is a rectangular prism. 300 centimeters by 12 centimeters. The volume of a rectangular prism is given by length times width times height, that is 3 centimeters times 200 centimeters times 12 centimeters. This is centimeters. This is the volume displaced. Now we need to calculate has a 1 gram that 700 of 120 that into kilograms. Weight 20 kilograms. Weight 700. Huge since because in that is that ship the submarine